everyone. This tiny pellet, about the size of a gummy bear, can produce as much electricity as a ton of coal. But if you dug uranium out of the ground and tried to use it in a reactor, nothing would happen. Turning that rock into nuclear fuel requires one of the most remarkable engineering achievements of the modern age. So, how do scientists transform ordinary uranium into nuclear fuel? The answer involves separating atoms that differ by just 3 neutrons, using machines spinning faster than jet engines, a process called uranium enrichment. For centuries, miners in the mountains of Central Europe kept running into a strange mineral. It was heavy, black, greasy, and completely useless. They called it pitchblende, and it kept getting in the way of what they actually wanted: silver. So they threw it away. Then, in 1789, a German chemist named Martin Heinrich Klaproth decided to study this mysterious rock. Inside it, he discovered a brand new element. Inspired by the recently discovered planet Uranus, he named the element uranium. But Klaproth had no idea what he had really found. For nearly a century, uranium's most popular use was decorative glass. Add uranium salts to molten glass, and you get glowing yellow green glassware known as uranium glass. Which means that for decades, people unknowingly decorated their homes with a mildly radioactive element. Probably not the safest interior design trend. But the real mystery of uranium wasn't discovered until the late 19th century. That's when physicists like Henry Becquerel and Marie Curie realized something extraordinary. Uranium atoms were constantly releasing energy. Not because they were burning, not because of chemistry, but because the atoms themselves were unstable. That discovery would eventually lead to nuclear physics, nuclear power, and nuclear weapons. But first, scientists had to solve a strange problem hidden inside uranium itself. When scientists looked closely at uranium atoms, they discovered something surprising. Natural uranium isn't made of just one type of atom. It's actually a mixture of two isotopes. Isotopes are atoms of the same element that contain different numbers of neutrons. You can think of them like two siblings. They look almost identical but behave very differently. The first is uranium 238. It makes up about 99.3% of natural uranium. It's heavy, stable, and not very interested in splitting apart. If uranium were a team project, uranium 238 would be the guy doing absolutely nothing. The second isotope is uranium 235. It makes up only 0.7% of natural uranium. But uranium 235 has a special property. It's fissile. If a neutron hits its nucleus, the atom can split into smaller atoms called fission fragments. When that happens, two things are released: a huge amount of energy and more neutrons. Those neutrons can split other atoms, which splits more atoms, creating a chain reaction. And that chain reaction is what powers a nuclear reactor. The problem is, with only 0.7% uranium 235, natural uranium usually doesn't contain enough fissile material to keep the reaction going efficiently. So engineers had to figure out how to increase the concentration of U-235. That process is called enrichment. Separating uranium isotopes turns out to be incredibly difficult. Chemically, uranium 235 and uranium 238 behave almost exactly the same. They react the same way. They form the same compounds. They even look identical under a microscope. The only difference is weight. Uranium 238 is just 3 neutrons heavier. To exploit that tiny difference, engineers convert uranium into a gas called uranium hexafluoride. That gas is then fed into machines called gas centrifuges. Each centrifuge is a tall, narrow cylinder that spins at incredibly high speeds, often tens of thousands of revolutions per minute. Inside the spinning chamber, physics takes over. The slightly heavier molecules containing uranium 238 move outward toward the wall. The slightly lighter molecules containing uranium 235 remain closer to the center. Pipes extract that slightly enriched gas and send it into another centrifuge, then another, then another. One centrifuge barely changes the concentration, but thousands working together, a system called a centrifuge cascade, can gradually increase the percentage of uranium 235. It's a process that requires extraordinary precision because if one centrifuge fails, it can quickly turn into a very expensive metal blender. Uranium isn't enriched to the same level for every purpose. The percentage of uranium 235 determines how the material can be used. Natural uranium contains 0.7% uranium 235. Most commercial nuclear power plants use low enriched uranium, typically around 3 to 5%. That's enough to maintain a controlled chain reaction inside a reactor. Some research reactors use uranium enriched to around 20%, but when enrichment reaches around 90%, uranium 235, the material becomes weapons grade uranium. And that's where global politics enters the picture. Because the same centrifuge technology used to produce fuel for clean electricity can also produce material for nuclear weapons. The difference can be just a few more spins of the centrifuge cascade, which is why uranium enrichment facilities are among the most closely monitored industrial sites on Earth. Uranium began as a rock miners once threw away. Today, it powers cities, drives submarines, and sits at the center of some of the most important technological debates on Earth. Turning that rock into nuclear fuel requires a process that separates atoms differing by only 3 neutrons, a tiny difference with enormous consequences. Because in the end, uranium enrichment is a reminder that some of the most powerful technologies humanity has ever built depend on changes at the smallest scale imaginable. So, the next time you hear about nuclear fuel, remember the difference between an ordinary rock and one of the most powerful energy sources on Earth comes down to just 3 neutrons inside an atom. If you enjoyed this video, please like and share it with others who enjoy learning about science and technology. Don't forget to subscribe for more videos exploring the technologies that power our world. Thanks for watching.